mechanics and our friend Newton. Good friend Newton. Ready?
No.
Come on, what's the problem?
That's not ready.
Okay. Newton's three laws, please. You've already seen one of the laws, Newton's second law. What's that?
That is
F equals ma. Okay. Now, let's start. Okay. So, there are three laws. Great. It's because you're on your phone. Come on. You make me angry like Hulk. You know Hulk?
Maybe.
Ah, you do know Hulk.
No.
He turns green.
Yes. What's the issue? Hulk.
Yes, that's what I said. Hulk.
Okay.
Alright. You got it? Right. Newton's first law says that if a body is at rest, it will stay at rest, or if it's in motion, uniform velocity that is, it will stay in uniform motion unless it's acted on by a force. So what I mean by that is, if it's at rest, it will stay at rest unless a force acts on it. Or, if it's moving with a constant velocity, it will continue to do that until a force acts on it. Okay? So this is Newton's first law. For the exam, you do need to know these three laws, because sometimes they do ask you for the three laws. So this is the first law. Yeah? Yes? Okay. You don't need to draw this, but it helps you to understand the first law. So, an object is at rest, will remain at rest, unless it's acted on by an unbalanced force. An object in motion will continue with constant speed and direction unless acted on by an unbalanced force. So like with the football, the ball is at rest until a force is applied, and then it will continue in constant motion until another force acts on it. Yeah? Get the idea? Okay, so Newton's second law, you know this one already. Force is the product of mass and acceleration. F equals ma. Come in.
Morning, Stephen.
New student?
Are you a new student,
Ah,
Sean
yes.
Patrick?
What happened to you? I was expecting you at like 10 o'clock. You getting lost?
Yeah,
Which
we're getting
is
lost
still
due to the link.
That's okay.
Okay.
Take a seat. We're just started a new topic.
Okay.
Newton's three laws.
Name's Sean Patrick, like my son.
Oh, look here, you'll appreciate this one. For Newton's first law.
Will remain at rest unless acted
Can I
on
take the
by
first one?
Yes, sit anywhere, yeah.
Yeah, thank you.
object in motion will continue with constant speed and direction.
Relevant for Sean, maybe.
Yeah, but he wants to stop that ball before it hits the net.
Oh, yeah. Yeah. Well, then he needs to be the unbalancing force, doesn't he?
He's very unbalanced.
Alright.
Like that.
Yes.
Okay.
Okay, so that's the second law. So you're kind of coming in at the start of the next lesson. We're just doing Newton's three laws. Have you got pen and paper?
Yeah.
Yeah. So you might as well just take down where we're at, and then you can get the notes that you missed later. Okay. So this is Newton's three laws. Did you write down the second law? Yeah. Okay. So as a picture, the force is a product of mass and velocity. Yeah. Okay. So last law, Newton's third law. So Newton's third law, for every action, there is an equal and opposite reaction. Okay. So write that one down, please. Shamu, isn't it?
Shalom Patrick.
Yeah. If I say Shamu, is that close enough or way off?
Yeah, it is close.
How do you spell it?
SHAROON. And
Sure.
okay, you can call me Patrick. I'm good with that.
Patrick?
Yeah.
That's
Okay.
easier. I just actually need you to move a couple of seats so I can see the person behind you. So just a little bit. Yeah, yeah.
I can go to the end.
Doesn't have to be the very end.
This one?
I'll do.
Thank you.
So you must think carefully now. If you tell teachers they can call you Patrick, then it'll be Patrick forever now.
Yeah, it's
okay. That's all right. All right. So everybody, this is Patrick now. Okay. You're from Pakistan, isn't it? Yes. Yeah. This isn't your first class though. You were in class. Yeah. You had class yesterday,
Yeah,
didn't you? With EAP, was it?
yeah, it was. I actually didn't miss Ma'am Sylvia, so that's why it wasn't. And I didn't know
Oh no,
anything
that's
about
okay. Yeah. So this isn't your first class though.
Yeah,
Okay. That's
obviously
okay.
it's my first time.
All right. Did you write this down? Yeah. I'll just tell you first though, the person behind you is a troublemaker. You stay away from her. Trouble. No? Alright. Next now. So this is an example of the third law. So air is pushed out at the back of the balloon and the balloon is pushed forward. So this is action and reaction. Okay. Yeah? Alright. Right. Some definitions, more definitions. The reaction force is the force provided by the reactant object. So what does that mean for this example here? You got that? Not yet. Yeah. A triple plus. Okay, so for example, like here, there's a weight force pulling this down, as you know. So the weight pulls it down, so it should continue to move. But of course here it stops. And the reason it stops is because the table is providing an up force that will cancel this down force. So this is the weight and this is the reaction. You get that? Yeah. And it's the same with the wall. So here I'm pushing against the wall. So my force here is cancelled by the wall, which is pushing backwards at me. Okay, so this is my force, and then the wall force is a reaction force. Yeah. Okay. Do you have this? Amanda? Yeah. Okay. So here's our first example. So everything's just been definitions. Write this one down. It's a simple example to get us started. Okay, can I do this one? No? Yeah. So, for this example, there is your tabletop, there is your block, or what is it? Block. Nothing exciting. 20 kilograms. So, as you know, there's a weight force down here of W. That should equal mg, which is 20 times 9.81. 20 times 9.81. So that's 196.2 newtons. But of course that's not the only force on it, because if that was the only force it would start to move down. So there must be a balancing force upwards called the reaction force, and this must equal 196.2 newtons as well. Otherwise the block would move. Actually, Patrick, now, so I don't forget, do you know what Moodle is?
No.
Has anyone talked to you about Moodle?
No.
Anybody want to explain it to him?
Yes.
Our website,
Yes? Go on, tell him.
we can learn everything.
Well, maybe it's not as good as that. Um,
It's just a website that has notes and homework and all
yeah,
that.
it's the school's website where we put the notes and resources and stuff. So you want an account to this. So what you need to do to get an account is you need to email me.
Steven dot SBI.
Uh, you need to email me and just put Moodle as the subject, and I need 3 things from you to make your account. I need your email, your full name, and your date of birth. If you give me that, I'll make your account.
After class?
Send me an email whenever you get a chance to. Whenever, yeah. No rush. I mean, if you make it today, then I will try to make your account today. All right. Next question. Yes.
Mhm.
Okay. Right. So write this one down, please. So much English.
No.
Oh, did you finish your presentation?
No.
No.
Did you start it yesterday?
No.
No.
It's for tomorrow, right?
Yeah.
How to do conclusion.
First do everything else, then do conclusion.
In conclusion, I say everything. Say some.
Yeah, kind of. Are you doing your presentation in EAP class?
Yes.
And who's your EAP teacher normally?
No, I don't know.
Kono, Kano, I don't know.
Connell and
Connell.
Dennis.
Well,
Connell
we
and Dennis, or
No, Connell is the main guy.
But the time that you have tomorrow, who is normally teaching you at that time?
Maybe
Dennis.
Kono.
Dennis working.
Dennis is
It
today.
is.
Oh, today.
Today is
Dennis.
Dennis.
Tomorrow,
Tomorrow is
Connell?
Dennis also.
Tomorrow maybe it's Kono.
No, tomorrow is Dennis.
That's good news for you.
Huh?
Yeah. And
Ooh.
but it's gonna be more than one teacher, so
Yeah.
not so much of a relief.
Look, look
Look directly at Dennis.
Dennis.
Look
Yeah.
Dennis eyes.
Yeah. Because Dennis asks nice questions, you know, like, what have you learned?
Mhm.
What would you like to learn? Things like this.
What about Kono?
Oh no. No, no. Bad questions.
Yes.
Oh, last time he asked one day to uh try find a way to tell Kono what his periodic table is. And he said, "Oh, I'm just a children. I'm 7 years old. I don't understand."
So he said, explain it to me another way.
Yes.
Uh,
And they try most very more time and no, and they give up.
yes, I understand. Which student was this? A science student?
Yes.
Yeah. Okay, do you have this?
No.
Not yet. You got this? Not sure. Yeah? Grace?
Oh, this one.
Uh-huh.
Yes.
Yes?
Yes.
Okay. So what's happening here in this example, the block is how much did I say?
200
200 kilograms, okay. Now there's a weight of course which is mg, so if we calculate it, 200 g, so this is 1962 newtons. But in this one there are two forces going up. There's a reaction force, or, and there's a force of a man pulling it up of 1000 newtons. You know what a man looks like. There.
Nice.
Nice. Now, in this one the idea is the same. The block doesn't move, so that means or plus 1000 must equal 1962.
All that. Right? Because the block doesn't move.
No, it must be balanced, because if it was
Oh.
less, then it'd be
Oh, yeah,
moving
yeah.
down or up. Yeah. So then or must equal 962 newtons. Yeah.
Yes. Evidence.
For this question, the question was longer than the answer, I know, but it's good for your English. Yes. Okay. Next example. Yes. Yes. Okay.
No, many, many more.
Hang on. You don't have to write it all down. I can draw the picture for you. Okay. And then there's this one and this one. Okay. 1, 2, 3 more questions. I'm going to do this one at the end because it's longer. So I'll do the shorter ones first. So this one here, you don't need to write the information. It's just like the last one, except the rope makes an angle of 45. Okay? So, in fact, I'll just change this one. So this time, the rope is at an angle of 45, but it's still 1000 newtons. The man is pulling this way. The angle here is 45 degrees. So there's a force this way, and there's a force this way. This is 1000 cos 45, as you know. So that is 707.1 newtons.
But we don't have to care about that, right?
Let me read actually the question. 707.1 newtons. So here, yeah, again, whoops, sorry. I want the or. So this time, or plus 707.1, what should that equal?
1962.
1962. So the or here is 1962 minus that. So that is 1255 newtons. Is this block moving though?
No.
Are you sure?
Because it is equal.
It is moving because in the question it says he's dragging. But if you look at the picture, look at the forces, look. This force cancels this force, but there's now a force to the right.
Right.
Is there any force to the left?
No.
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 Friction.
There might be friction, I didn't say. So the block is actually moving this way. Yeah? In fact, if you wanted to, you could calculate the acceleration. Do you know the mass of the block?
200.
Yes. Do you know the force?
Yeah.
Yes, 707. So could you know the acceleration?
Yeah.
Easily. Okay. And next example? Yep. So the next one, it is the same, except I don't tell you the mass. So it's the same picture this time, but I don't tell you the mass. So here, the only thing we don't know is this mass. So I'll just call it M. So here we don't know the mass. So I'll just say mg. Okay. And most importantly, which is different to this question, which you should note please, the block moves at a constant speed. So I'll write that down here. The block moves at a constant speed. And also what's different in this question is there's some friction force here. I'll just call it D as well. Okay, so these are all the forces. Yeah? Yeah? So I'll just scroll down a little bit. So let me just draw this again. There are four forces. Going up is or plus 707.1. To the right is 707.1. Going down is mg. And going left is the friction force, the drag force. Now, because the block moves at a constant speed, which of Newton's three laws is that one? First, second, or third? First. First.
Because
But there is no A.
yeah,
It's moving at a constant speed.
Newton is
So Newton's first law says it will move at a constant speed if there's no net force. So Newton's first law says that the up force must equal the down force, they must cancel, and the left force must equal the right force, they must cancel. So it can move at a constant speed. So Newton's first law says that R plus 707.1 must equal mg, and D must equal 707.1. And my question was, what is the friction force and what is the reaction force? Okay, so you can see here, this is the reaction force. Sorry, the friction force. And the reaction force, what will that be? That will be mg minus 707.1. Yep. Can we know what the exact number is here? No, because I don't know what the m is. So the answer just stays like this. Yeah. I suppose I could have changed it and put in a number, but that doesn't matter. Okay. 7. Right, okay. Can I continue? Yes?
Yes.
Yeah, okay. Right, so now this long one. So we'll finish on this one. Again, it's a lot to write down, so I'll just draw it for you. You don't need to write it down. A weighing scale measures reaction rather than weight. You place a half-kilogram book on weighing scale. The weighing scale is then lifted vertically up in the air with acceleration of 1 and then is dropped onto the table. Alright, I'm going to change that. It's too long. Too long, right?
Yes.
We'll make it shorter. Um, and you know what? I'll give it a number here. And here it is here. Oh. Right, let's see. A weighing scale really measures the reaction person. Book is placed vertically on the weighing scale. The weighing scale is then lifted vertically up in the air, and then what would the reading on the weighing scales be as it is accelerating upwards? Okay. Right. So I'll change this a little bit. So you all have a weighing scale at home, maybe? Yeah?
Yeah.
And the weighing scale, what unit is on it?
KG.
Kg. Now in fact, it really shouldn't be kg. It should be newtons, because it's measuring weight. But in fact, it's not even measuring weight. It's measuring reaction. Let me explain. So for example, here's your weighing scales. Weighing scales. You know what it looks like. Okay. So if I put 1 kilogram on it, your weighing scale says 1 kilogram, right? But it's a weight, so it really should say what?
10 Newtons.
Yeah, about 9.81 newtons. But what would happen to the weight if I gently lift this? Now, please note, I don't take it off the scale. So for example, imagine this is 1 kilogram, and I put it on the weighing scale. It will say 1 kilogram. It should really say 9.81 newtons. But if I gently lift this, but still leave it on the table, what would happen to the number here?
Decrease.
Decrease.
Decrease, yeah. So it's not measuring the weight, it's measuring how much the weighing scale is pushing up on it. Okay? And what would happen if I push down on it?
Increase.
It increase, because the weighing scale is reacting more. You get the idea? So my weighing scale should really say newtons. Your one will say kilograms. Okay? So what's happening here? It's half a kilogram. Okay. So for this question here, this is actually not 1 kilogram, but rather it is 0.5 kilograms. So you can draw this. And then what happens is I move all of this up in the air at 1 meter per second squared. So before I do the question, what do you think will happen to the number?
Increase.
Increase or decrease?
Decrease.
Decrease.
Increase.
Let's see. So you're saying, Patrick,
Decrease. It should decrease.
increase or decrease?
Decrease.
Decrease. If I move this up, what will happen to this number on the weighing scales? Will it increase or decrease? What do you think? Decrease?
Same number.
Same number, good. Another option. What do you think?
I think it'll increase.
It'll increase? Increase. It will increase. It'll increase. Because what's happening is it's like the weight is pushing in more.
But it's inertia, right?
Well, we'll calculate it exactly now. Yeah. So if you have this here and you're pushing up,
So you feel a little heavy?
it like feels heavier. It feels heavier. Let's
Where's
calculate it.
my hand?
Under the weighing scales.
And when the weight scale?
Yeah, so here's the weighing scales and then here's the weight. And you're pushing it up together. Yeah?
Why?
Why not? Okay. So let's have a look here. So let me just draw it again, but kind of simpler diagram. So here it is here. There are two forces acting on this. The weight going down, which will be 0.5 g, which is 0.5 times 9.81, which is 4.905 newtons.
By 0.5.
Well,
Half a kilogram times g. The weight is
You
mg.
have to change it to kilograms, right? And
No,
then
I'm just calculating the weight is mg.
okay.
The weight is mg, which is this. This is the weight.
But the mass has to be in kilograms, right?
Yeah, I said it was half a kilogram.
Oh, okay.
Yeah. This picture's messed up. It's half a kilogram.
Okay. Yeah.
Okay, that's okay? Alright. Now, there's a force going up. Like if you're looking at the weight, oh, my pictures are so ugly. If you're looking at the weight, it's 4 point, no, what did I say it was? 4.905 newtons. And there's a reaction force going up here. You don't know what this reaction force is. Is it bigger or smaller than 4.905?
Equal.
No, not equal.
Why is it not equal?
Smaller.
But it's not moving.
It is moving. It's moving up at 1 meter per second squared.
Okay, so it'll be bigger.
Yeah.
No, it'll be smaller. The upward force will be.
Sorry, yes, that's what Amanda said. Smaller. So the or should be smaller than 4.905. So what is the total force? Or minus 4.905. And will this equal 0? No. In fact, it equals the total force. Yeah? Do we know the M? We do. MA equals or minus 4.905. What's the A?
1.
1. Very good. And the M? 0.5. So the reaction force, let's calculate it. 0.5 minus 4.905. Sorry, 0.5 plus 4.905. 5.405 newtons. So we're nearly finished. Next part. I need to scroll down a little bit. Yes? Can I?
why R is smaller than 4.9?
Because if R was equal to 4.905, it won't be moving.
But what is the
If
R?
R is smaller than this number, it will be moving up. And if
R is bigger.
no. Sorry. Of course. And I can see it's bigger right here. Sorry, Amanda confused me.
Isn't it supposed to be 4.905 minus R?
R should be bigger than this, which it is.
Yeah, okay.
Yeah. Okay, next part.
Why is bigger?
Because it's going up. So like if you have this here.
Ah, so we have, so the I is
Yes.
become bigger.
Yes. Okay, can I do the next part?
So if I just move down, the W will be bigger?
Yeah, the R will be smaller.
Mm.
Yeah. Okay. Can I go down?
Yeah.
Yep. So this number here will be important. So for example, if, remember at the start I have 0.5 kilograms, what's the weight? It is 4.905. Here, I don't know what the weight is, but the weighing scale thinks the weight is 5.405. So it thinks it's bigger than it should be. How much bigger? Well, let's calculate it as a percentage. The weighing scale thinks it's 10% bigger because the reaction force is 10% bigger. So it won't say 0.5 kilograms anymore, it will say 0.55 kilograms. So as the weighing scale is being moved upwards, the weight will appear to be 10% bigger, which means the weighing scale thinks the mass is 10% bigger. If this was going down, what do you think the result would be?
Less.
Yeah, maybe about 45 kilograms.
Mhm.
Now you can do this at home. Does anyone live on campus? Great. Do you have a weighing scale in the bathroom?
No.
You could get a weighing scale,
Okay.
take it into the lift, stand on the weighing
But the
scale.
lift is like really slow, so I don't think there'll be a big difference.
I think you'll notice it. Start at the ground floor and go to the top floor. As you go up, you should see your weight increase,
Like
and
it
then as you
stops
go
again.
down, stops, it will go back to normal, and then
Mhm.
as you go back to the ground floor, it will decrease.
Okay.
No weighing scales?
No.
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 I'm poor.
Good. Let's see how fat I am. Now that I'm eating a lot.
Yeah, but just travel downwards and it will be less. Okay. I can close this now? Yeah, so let's see what you had to do.
Bye bye.
No, your homework now.
Bye bye. See you.
Tomorrow? But well,
No.
let me put your homework up.
No, don't let me see it. Sometimes I can't see anything.
Right.
Oh, that's so fast.
You can
Nice.
the questions are short, aren't they?
Yeah, but
Yeah.
I
No.
spent 2 hours to do this.
2 hours? No.
And you spend
Maybe
half an
3 hours.
hour.
I
5 minutes,
don't know.
one question.
Yeah.
You and
Translate,
yes.
email to the teacher,
But it's good for your English.
presentation,
It's
No,
good for your
no, no,
English.
no, 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 no. Makes me want to die.
Okay.
Bye bye.
Do you have your phone? You can take a picture of these questions. You did that already?
Yeah.
Oh, great. Okay. Can I close this now?
Yeah.
Yeah.